CS 402 on Wednesday, May 28th, 2014.
So I didn't bring the roll sheet because I just found out I don't have a printer. So I came to school and said, well, where do I print? So if I forget to bring it, everybody get credit, whether you are here or not. So you get 1 point, for today. All right, warm-up number 1 is due at 11:45 next Thursday, June 5th. Okay, so the deadline is at 11:45. There's 15 minutes of grace period, which means that if you submit within 15 minutes of the deadline, it's not considered late. Okay, so it goes all the way to midnight. Okay, and all the deadlines are 11:45 p.m. I said it that way so it's more obvious when I say which day is the deadline. I'm going to mention this every time in every lecture. If you have code from previous semester, be careful not to copy the code from it, and the best is to get rid of it. Okay, please review the lecture 1 slide that talks about my policy regarding plagiarism and stuff like that. Okay, and you're expected to start all your assignments as early as possible. So for warm-up 1, I do expect you. Or many of you should finish it by this weekend so you can submit early and get, I guess if you submit 72 hours, 3 days before the deadline, then you get 10% extra credit. I expect most of the people want that 10% extra credit, which means that you will have to finish, by the end of Monday. Okay, so this weekend, so if you haven't really started, you're really starting too late. And as we, move forward in the semester, it's really a good idea to finish things really early, okay? And I do expect you that it's summer. There's, you shouldn't be doing anything else other than, working really hard, on this class. I don't expect anybody to take more than 1 classes. You should do things early, okay? If you are stuck, you should come to see me during office hour, and I posted an email to the entire class through the class Google group yesterday saying that my official office hour now is on Monday and Wednesday from 1 o'clock to 2 o'clock. I just got my key today to PHE 333. And so usually I don't get too many visits during my office hour. So what I would do is that I will be there for sure for the first half an hour. And if nobody shows up at the end of half an hour, I might just leave. Okay, so if you know that you're not available during the first half hour and want to see me during the second half hour, make sure you send me an email so I will stay, during the second half. All right, otherwise, nobody there, I'm going to be gone. Also, feel free to discuss over the class Google group, okay? And again, you have to sort of follow the rule that I set up. If you post something to the class Google group, you can't address your email as if you are talking to me. You have to be talking to your classmate, okay? And anything that gets posted to the class Google group, I might respond, because sometimes when the volume gets high, I might miss something. So I will try my best to respond, all right? Especially for warm-up 1 and 2. For the kernel assignment, I'm going to talk about the rules for the kernel assignment a little later, okay? All right, the spec for warm-up 1 may have updates, so make sure you check, the spec. So what happens is that I change anything in the spec after the spec was posted, I will use a blue text that looks like this. I'm going to say BC : to say that, I'm changing this after the spec has been posted. Okay, so usually I will make an announcement to the class Google group, and I see that some people are not on the class Google group, so maybe you have missed some of the announcements. So make sure you just check the spec. Don't print them out, okay, because print them out, it's going to be outdated. Okay, so make sure you, look at the stuff online. And again, a reminder of something called grading guidelines. Grading guidelines tell you how we're going to grade. Okay, and we tend not to change the grading guidelines. Once it's out, we sort of stick to it. We might change the data that we use to grade your assignments, but the script is not going to change. Okay, so all right, so grading guideline is the only way we will grade, and we can only grade on, for warm-up number 1 and 2, we can only grade on nunkey.usc.edu in our grading account, which you don't have access to. Okay, so you got to make sure that your program runs perfectly anywhere on nunkey.usc.edu. Okay, make sure your code doesn't have any kind of a strange dependency that has to be run from your account. Okay, so usually that's not a problem, but if you start writing code, I mean, the expectation is that you wrote every line of your code, so if you're doing something weird, you should know. All right, so don't make your program depend on something in your home directory or in some, some weird stuff. All right. And if you have, and you're supposed to start looking for kernel partners. So, if you find some potential kernel partner, you say, hey, can I run my program in your account just to make sure I don't have any dependency, and verify that in that way. Okay? If you have other friends that have accounts, you can also ask them to do that. All right? So therefore, it's a very good idea to run your code against the grading guidelines and run them on nunkey.usc.edu. Okay? If your program worked perfectly on your laptop, it doesn't mean anything because, due to our fairness policy, we can only grade in one place and using only one grading policy. All right? You need to learn Unix on your own. In the end, our kernel assignment is to implement a Unix system, so you have to know what you're implementing. You got to get used to reading man page and those kind of stuff. You need to know what does, command line arguments means and all that kind of stuff. Okay, so we have a tutorial on the class webpage, right? So make sure if you're not familiar with Unix, you should read that. Unix is very similar to Linux. Okay, and in the end, the operating system we're implementing is something called Unix. So it's kind of like Unix, kind of like Unix, kind of like Linux, but it's none of those two. But it's all very similar. Okay, so you sort of need to get familiar with these things. You should install Ubuntu 12.04 and maybe use it for warm-up 1, but make sure that you port your code to run on nunkey.us.edu before you submit your code. You should start looking for partners. You can work with your potential partners for warm-up 1 and 2, but you need to work at a high level and not write code together. You can do all the discussion, but in the end, when you write code for warm-up 1 and 2, make sure you write it completely on your own. Okay? If you're part of the Google group and you use your Gmail address, please do not set your class Google group email delivery preference to no email. Okay, I mentioned last time because all important announcements will be sent through the Google group. Okay, if I see that you're doing that, I will change it to all email so you make sure you receive everything. And if you don't want to read them, what you should do is just set up a filter so that they get filtered out. Okay, I see that some people still are not belong to the class Google group. Please, it's your responsibility to make sure that you're on the class Google group. All right, so and because all the important announcements will be sent there. And I have sent invitation to everyone. The invitation sort of expires in a week. So if you didn't accept the invitation or didn't follow the second option to register for the class Google group, send me an email to see how it can be resolved. All right, you have to be on the class Google group. If you have questions, please do one of the following, sorry about the typo, and not both. Post to the class Google group or send me a private email. Okay, the disadvantage of sending me a private email is that I have a 24-hour email turnaround policy. If you post to the class Google group, your classmate might respond, right away. Okay. All right, finally, in lecture 1 slide, I mentioned that you need to do this, okay, and I really want you to do this. So follow the procedure over here. So provided you have finished the first part of your warm-up number 1, you're going to do the second part. So list test is working, okay, so I want you to run GDB against list test and try to do this thing. And here's a very important step that you have to do. draw a picture on the paper to draw out your data structure. Okay? Change the number of items to 64, from 64 to 3, because you don't want to draw a list of 64 items. That will take forever. Right? So change this program so that list test only randomly generate 3 things. Okay? And then draw the picture to see what it's supposed to look like. Okay? So in this class, it's very important to understand the difference between the memory, the address of an object, right? And again, object and data structure are the same thing in this class. So you need to know the difference between the address of an object and the content of an object. Okay? So make sure you notice the difference between the time when you use the ampersand, which means address of an object, and see what it means, versus you try to print the content of an object. Okay? Draw the picture, make sure that everything matched up. Make sure you understand what is an address and what is a pointer and what does it mean to dereference a pointer, etc. Okay, make sure you go through this exercise. All right? If you already are expert in C and pointers and stuff like that, this should take you, no time. All right? So make sure you do this. All right, and every lecture I will start with a housekeeping, set of slides to remind you of deadline, and things like that. All right? So now let's go back to chapter 1. So by the way, this class is going to feel like the lecture is that we're going in a hurry because there are some deadline that we have to meet. There are several deadlines. One is the deadline to start you off with warm-up number 2. So we need to actually finish most of chapter 2 by next Monday, so you can start, your warm-up number 2. And then I got to get you ready for kernel number 1. So pretty much we have to finish all the way to chapter 5 to get you ready for kernel number 1. And then we're going to be racing to finish chapter 7 so that we can get you ready for kernel number 3. Okay, kernel number 2, you don't really need to get ready for, because it's kind of in a way it's an easier assignment because there's nothing really weird in kernel number 2. Okay, but 1 and 3 are really weird. All right, last time we were here talking about, operating system is trying to provide abstraction, and we talk about some examples, right? The abstraction for hardware are, operating system. So disk is abstracted away as files. Memory is abstracted away as program or processes, and the processors are abstracted away as threads of control. Okay, and we sort of mentioned that sometimes we're going to use the word program to mean process, to mean threads. So the word program sometimes could be ambiguous, but that's okay. Okay, so really have to interpret the word program in context. All right, the file is a very simple abstraction, right? I mean, we all deal with files. There's a hierarchical naming convention, and then you try to open a file, you read it, and you write to it, etc. In reality, the hardware is very, very complicated. Okay, the file could be sitting on hard drive, right? This is the icon for hard drive, or it could be sitting on a CD-ROM or a USB device, all kinds of storage devices. And then the files is going to move from the disk into memory, and then eventually you can access memory. Okay, the reason it has to go into memory because there's no way to access the disk directly. Okay, so the kind of operating system that we deal with, in order for you to access any part of the file, well, the file has to be moved into the memory first, and then you access memory directly. Okay, when you learn the processor class in computer architecture, you sort of learn that, the way for the CPU, the processor, to do anything, what it can read and write memory locations, okay, there's really no way to read and write the disk directly. All right, so therefore we have this abstraction. Okay, the abstraction is very nice and very simple, but of course it comes at a price that in order to get this all to work, it's very complicated. Okay, so part of this class is sort of to explain to you how does it actually work. Okay, we're going to create this abstraction. In reality, we have to map it to the hardware that actually can look very, very complicated. Some of the issues with the file abstraction is that we have to name these files. Okay, the files will be sitting on these devices, inside memory, on disk, and stuff like that. And we want the naming of files to be independent of what the devices look like. Okay, so this is called device independence. So that's one of the important issues that when we name something, we've got to make sure it's device independent. Okay, And these days, we know that all the file system, you sort of have a hierarchical naming convention starting from root, and that's how you name something. Okay, eventually you have to map that path, starting from root all the way to a particular directory, subdirectory, and to a file, map that to a physical device. Okay, so that's what we're going to see how that's getting done. We need to manage the space on the disk. Okay, the disks are a permanent storage device. Okay, once you store stuff onto it, it remembers it, so later on you can come back and retrieve it. Okay, so when you need to put stuff on the disk, actually it does matter how you put stuff on the disk. Okay, what it will affect is that depends on how you put data on disk, it will affect the speed of how fast the disk looks to you. Okay, if you put it in the wrong way, the disk system is going to look really slow. If you put it in the good way, then it's going to look very fast. Okay, and also, you don't want to waste too much space on the disk. So therefore, we're going to study trade-off regarding how do you put stuff on the disk. Some of the methods are more wasteful. Some of them are not. And usually, we're going to have the speed and space trade-off. The faster that you want, the more space you waste. The more compact that you want things to be, then you end up to have a slower processes. Okay, so that's sort of the usual trade-off. And also, we need to shuffle data between the disk and memory. Okay, so it turns out that that's a big problem because that, if you don't do it correctly, your system is going to perform really slowly, right? Because in the end, the processor can only access memory. So you really need to move data very, very fast from the disk to memory. Okay, so how do you really do that? That's one thing that we have to look at. And finally, your machine crashed. So if you are trying to write to the disk, and somehow the operation didn't get finished because your machine crashed, you lose power for whatever reason, the write to disk didn't get completed. Okay, so when you reboot your operating system next time, some of the stuff on the disk become inconsistent. Okay. Because you might be writing to multiple disks. Some of the stuff go onto this disk, didn't go to the other disk. Even on the same disk, you're writing to multiple places. So what if, part of the disk got updated and the other part didn't get updated? Okay? So in order for us to recover from these kind of crashes, we're going to talk about mechanism for coping with crashes. Okay? And most of this stuff we're going to cover in Chapter 6. All right? Even though in the introduction material, we're going to talk about, some of the backgrounds. What about the abstractions for programs, right? When you write programs, like in warm-up number 1, you're going to use list test, which is a program. You're going to write warm-up 1, which is a separate program, right? So when you write your program, you sort of have the abstractions that your program has an address space, okay? And the address space will look like this, okay? So this is what an address space looks like. On a 32-bit machine, right, the low memory address starts at location 0. And for 32-bit machine, the high memory address stops at 0xFFFF, right? I'm writing hex notation. So that's 32-bit. They're all ones. That's the last location in the address space. Okay? So the address space basically tells you what memory location are addressable. All right? So your program, so this is one way, your program might be organized, is that the executable code of your program are sitting at low memory address. Okay, after that, there is the data, segment. That's where you store your global variable, in the data segment. Okay, and then when you call malloc and stuff like that, you're allocating data in the dynamic region of your address space, or this is also known as the heap of your address space. Okay, so whenever you call malloc, an object inside the heap is going to get created. You're going to get a memory address that allow you to point to this object. Okay, and then you're going to store that memory reference somewhere, right? Maybe you can store it in the data area for your global variable, so you can keep track of these objects. Okay, another place where you can keep track of stuff is your stack. Okay, so this is your program stack, and the main purpose for the stack is to make function calls. Okay, you're going to write your program in C, right? The first function that gets executed in your program is called main. Okay, so this stack is going to, there's something called a stack frame. So the stack is divided into little stack frames, and every stack frame corresponding to one function. Okay, so your main function is going to be sitting here. As soon as your main call another function, what happens is that it's going to create another stack frame, and this is the stack frame that main calls. And that one, you can run that particular function. Okay, and that function is going to call another function, is going to call another function. So the stack keep growing this way, downwards, as you make more function calls. Okay, when you return from a particular function, that stack frame is going to get popped, and then you return back to the previous stack frame. Okay, and the reason we have a stack frame is because we want to store the local variable and the function arguments. Okay, so if you write a function, the function has function arguments, right? You write a function foo, okay, have a bunch of function arguments, and inside this function, you're going to declare local variables and stuff like that. Okay, these things, actually, all these variables, they live inside the stack frame. Okay, so for this function foo, let's say this is the last function that you're calling. This guy's foo. So therefore, all the function arguments, all the local variable, you can actually find them right inside of that stack frame. Okay, so when you execute a return statement from foo, when you return from foo, this stack frame is popped. So therefore, all these variables are automatically, they disappear. Okay, so that's why, these local variables, sometimes they are known as automatic variables. Okay, because the allocation is automatic. When you call this function, then all of a sudden they appear out of nowhere because they appear in the stack. Okay, you can use them. And when this function returns, they're automatically deallocated. Okay, so that's very different from the heap area. From the heap area, they are not automatic variables. They are managed variables. You, as a programmer, you need to manage them. Okay, so in order for you to create object in the heap, you got to call malloc. When you're done with that object, you want to free it. You're going to call free and return that particular memory location back into the space that's being managed for the heap. All right, so automatic variable live in the stack, and the not automatic variable live in the heap. Okay, so when you write your program, now you really need to pay attention to exactly where all these variables live. Okay, global lives here, dynamic lives here, and then function arguments and local variable live in the stack. All right, so this is your programming model, right? So this is the abstraction, the address space abstraction. As a programmer, when you write your program, this is the model that you have in your head. Okay, in reality, it's going to be very, very different. Okay, and in this class, towards the end, you're going to see exactly how this is implemented in the operating system. But for now, we're dealing with the abstraction. All right, so I'm going to put all the the data together, data, heap, and the stack. I'm going to call it data, right? Because they're all some sort of a data. Okay, so your program becomes when you're running it, right, there's code and there's data, and then you need to map it onto hardware. Okay, so over here, why does the disk show up again? Okay, if you want to run your program, the program has to be in memory. Okay, but once in a while, when your processor, when your machine gets too busy, you're running too many things, maybe we need to put some of these stuff, swap, you've probably heard of things like that. A program will get swapped out. Okay, when it gets swapped out, what happens is that this data and code will go onto a disk. Okay, because this program is not very active, or for whatever reason, we want to put this program to sleep. We put the entire program onto disk, and then we can free up the memory over here so we can use the memory for some other process. All right, so that's called swapping the process to disk. Okay, so therefore in this picture, we got to involve both memory and disk. Okay, in this case, the disks, they sort of go onto a funny place on disk because they don't correspond to a regular file anymore. Right, so this goes into the swap space of the disk. All right, so this is going to have some places where you can swap out a particular process. Okay, and over here, we also draw multiple processors because, this code might be multi-threaded. That you have multiple threads of execution that are executing right here. Okay, they belong to one process, one address space, but now you have multiple threads of execution that can be running in parallel. Okay, so when you have multiple processors, you can take advantage of that, so your program will appear to run faster. Okay. All right, when you have multiple programs, okay, how do you share them? You can try to cram them all into one memory, but that's really not very flexible. Okay, what we end up doing is that, we need to have multiple programs, even when they don't fit in the entire memory, we got to have a way to run it, in that piece of memory. Okay, and in the end, the mechanism that we're going to use is something called virtual memory. So the idea over here is that every one of these programs, the program has, code and data, right? Code and data. This guy has code and data, code and data. Okay, we're going to use something called the memory map. Okay, so this one draws like a map, right? So this is a memory map, M-E-M-M-A-P. Okay, the memory map will map the address space of this program to, sometimes it goes to memory, sometimes it goes to disk. Okay, so they go through this one basic mechanism to map the code and the data of your program onto, memory, so memory is called primary storage, and then the disk is called secondary storage. Okay, so there's this memory map, and that's what the operating system used to keep track of, all the data and the code of your program to see where, where they want to store all this information. All right, and virtual memory is the main topic of Chapter 7. All right, so eventually we're going to get there, and again, along the way, we're going to sort of starting to introduce you to the concept of virtual memory a little bit at a time. All right, and Chapter 7 is a full-blown, virtual memory. To share a processor, we can have a machine that only has a single processor. Okay, so this processor, it will run multiple, programs. Right, so in that case, what we need to do is that we use the concept of, you can think about these as virtual processor. Every program runs a separate virtual processor, okay, and the physical processor is going to be multiplexed among, all these, virtual processes. Okay, it could also be the case that all these virtual processors, they all belong to the same process. In this case, every one of them is going to be a single thread of execution. All right, so in that case, as we mentioned before, the abstraction of the processor is called thread of execution. Okay, so in this picture, it might be that all these three virtual processors belong to the same process. So basically, you have three threads running, each one of them running in one of these virtual processors, and they appear to be running in parallel. Okay, so when you have a program or you have a thread that's running, that means it's executing machine code, one instruction at a time. Okay, so the entity that's executing that code, well, that has to be the physical processor. Okay, so basically in this case, what you need to do is you need to create the illusion that when this thread is executing, it's running on this physical processor. Okay, so therefore, when this guy is running on this processor, is there any way for any other thread to be running in parallel? Well, it's not possible, right? Because you only have a single processor. Okay, so in that case, even if you have multiple threads of execution, you need to understand that, they might be multiplexed on a single processor. Okay, so even though they appear to be running in parallel, in reality, they will be, they might run in a single processor. Okay, but it's also possible when you have multiple processors, it is possible that all three threads, each one of them are executing on a separate processor. Because now you have more resources, okay, you can actually run each one of them in a physical processor, so your program will go 3 times as fast. All right, but when you do this, you got to make sure that this thread does not step on the toes of another thread, because otherwise, you're running two things in two different machines, right? Well, not two different machines, two different processors. These processors, they're really not aware of each other. Okay, so if this guy is going to go modify a global variable, okay, in the data in the data segment, and this guy wants to modify at the same time, you're running on two different processors. Well, you're allowed to do that. You're allowed to ruin your own program. Okay, so therefore, if you're allowed to do, so this is a very powerful abstraction. Okay, but when it comes power, then you got to make sure you do the right things. Okay, because otherwise, bad things can happen. All right, so it's good to have parallelism, but you also, you got to be able to control it. All right, because otherwise your program will go mad. Okay, and there's nobody who's going to stop you from your program going mad because it's your program. Right? If I have one program that has 3 threads that I wrote, and these threads want to kill each other, should the operating system stop them from killing each other? No, right? The operating system, that's good. Okay, the operating system just want to watch the show. Okay, so please keep that in mind. If you have multiple threads running in a single process, the operating system doesn't really get involved. All right? Okay, so you got to be careful. All right, So that's sort of and this is regarding chapter 5. Chapter 5 is processor management. Okay, so we're going to talk about, how does the operating system schedule a thread to run on a processor. All right? And we're going to talk about the single processor case, the multiple processor case. And one thing that you always need to keep in mind that, on the hardware, we might have a single processor, we might have a multiple processor. So when you try to solve a particular problem, you always have to ask, well, does the processor a single, does the machine has a single processor or multiple processor? Because the solution might be very, very different. Okay, I mean, from the point of view of the operating system implementer. Okay, but from the perspective of an application programmer, the application programmer shouldn't care how many processors are out there. Okay, when there's only one processor out there, the program needs to work correctly. When there are multiple processors out there, the program should work just as correctly. Okay, it might run a little faster, okay, but it should be just as correct. Okay, so therefore, it's the responsibility of the application programmer to write the program in such a way that no matter what the hardware looks like, it will always run correctly. All right, so that's, your warm-up number 2. Warm-up number 2, you're going to write multiple threads, and it's your responsibility to make sure that it always runs correctly. All right? Okay, chapter 1, they sort of talk about, all these technology was invented in the 1960s. The stuff that people worry about in the 1960s are, so I guess there are 4 things that were singled out. One is called multi-programming. Okay, so this is how to run multiple things in one CPU. Okay, the second thing they worry about is called time sharing. So usually when people are about time sharing, they're talking about an interactive user. Okay, in the good old days, the machine, you just submit job, they're running in a big machine room, and then you go, take a walk, have a cup of coffee, and eventually when your job is done, your operator is going to, call you and say your job is done. Okay, so that's a batch system. Okay, later on, they say, hey, wouldn't it be nice if we have an interactive system where you sit in front of the terminal and then you run your program. Okay, so in that case, your computer need to handle interactive user and the first type of user, which are called batch users. Okay, then sort of the issue becomes a little more interesting because the interactive user need to have good response time, and the batch user, they don't really care about response time because they are alpha coffee. 1960, they have to worry about the complexity of software, how to make as software get more complicated, how does the operating system accommodate the application programmer so that they can, the application programmer, they just want to program and solve their problem effectively. They don't want to worry about how to schedule, threads on processors. Okay, they want to be, completely transparent to what the hardware look like. Okay, so as the software gets, more complicated, the operating system has to support more feature in the software. And finally, they have to worry about security. Okay, the operating system got to make sure that if your system is running multiple, user processes, the user processes are isolated from each other, and also the operating system is isolated from user processes. As it turns out, 50 years later, we still worry about the same thing. Okay, what we worry about, or as operating system designer worry about, are multi-programming, okay, running things in parallel, except that these days we're talking about a server farm, okay, a parallel computer, a sort of parallelism at a different scale, okay, but still the same issue. We still worry about time sharing. We want to support interactive user, but now interactive meaning that you're running audio program, you're running video program, right? You're playing YouTube and all kinds of stuff. All these things are interactive programs, and they need good response time. Okay, so those are the stuff that we worry about. Software complexity, software gets a lot more complicated than 50 years ago. It's a much bigger problem than could be imagined in the 1960s. And same thing with the security problem. Okay, the kind of security problem we have today, 50 years ago, they couldn't have imagined, the kind of problem we have. All right, so the textbook, basically, they talk about a brief history of operating system. I'm going to skip all that. So if you're interested, when you have extra time, you should flip through it just to see, a little bit of the history of the operating system. Today, we have some of the popular operating systems. We have Linux, Unix. They're still alive and well. We have Microsoft. We have Apple. Okay, so this picture sort of shows you what kind of system that we have today. Okay, and also where do they come from, right? Today we have Android. Android is actually running Linux. Okay, whenever all these Android, they're running actually Linux. Okay, so Linux derived from Minix, and Minix derived from Unix, and Unix derived from Multics, and Multics was an operating system programming like it's an operating system of the 1960s. Okay, so it goes all the way back, and so Android is basically a version of Unix. Okay, if we look at Apple, Apple is running Mac OS X and also running iOS, and they all come from the system called Darwin. And Darwin is the one when Steve Jobs went back to Apple. That's one thing he started, is Darwin. And Darwin is basically Unix. Okay? Inside Darwin, it has two predecessors. One is FreeBSD, and FreeBSD come from this guy over here. Okay, so it's BSD is basically Unix. Okay, and the other thing is Mach. Mach at some point is also look completely like Unix. It's one of these branches over here. Okay, so when you're on a Mac, basically you can start a terminal. Okay, and the terminal looks pretty much like the Ubuntu terminal. Okay, because you are running on a Unix machine. All right. In Mac, there's the old architecture, not based on Darwin. Okay, so those are the Lisa and the Mac, and those systems are obsolete. Okay. Microsoft also had two versions. One is the MS-DOS and the Windows 3.3.x. Those things are gone. Right. These days we have Windows 7, we have Windows 8. Okay. The predecessor is Vista. Vista's predecessor is Windows NT. And Windows NT came from OS2, which is an IBM product. Okay, IBM designed their operating system from scratch. They call it OS2. And the other one is called VMS. Okay, so what happened is that VMS was an operating system. So if you go to the history slides, VMS was the operating system developed by the Digital Equipment Corporation, okay, or DEC. They were a very sort of a major player in the computer industry. They built something called the mini computers. Okay, in mini computer, they run two operating systems. One is Unix, and the other one is VMS. Okay, so VMS is basically Unix's little brother. Okay, there's actually a version of VMS that looks exactly like Unix. All the commands are exactly the same. Okay, so basically over here, VMS is also come from Unix. Okay, so basically what the slide is saying is that every day that we have today are pretty much Unix. Okay, and that's why the system that that we're going to use in this class is going to be Unix. Okay, once in a while, if you look at the textbook, sometimes they talk about Microsoft. Okay, but we don't really have time to cover two different operating systems. So in the summer for this session, most of the time we're only going to talk about the Unix part of things. Okay, so you need to understand that that's pretty much what the world looked like today. It's mostly Unix. All right. Or VMS, cousin of Unix. All right, a little background of C. We're using C. So in the 1960s, there's a program called CPL. It's the Combined Programming Language. It's developed in England, and later on, so it's a high-level programming language. Okay, they developed something a little more restricted version of CPL. They call it the Basic CPL or BCPL. Okay, and it was meant to do system programming. Okay, it was meant to design to be implementing to be used to implement operating systems. Okay, and then turns out BCPL was still too complicated. They further simplified it. They just call it B. Okay, and after B, the next version of B is called C. And in 1970s, and that's where we get the name C from. Okay, ever since the 1970s, Unix are implementing in C. Okay, so for the past 40 years, Unix is the language to implement. Sorry, C is the language that's used to implement Unix. Okay, and we're sort of going to see, why C and what is the difference between C and C++. Once in a while, we're going to talk about C++. And the basic thing about C++ is that C++ is a higher level programming language. So it's done in such a way that it provides further abstraction that hopefully that might be useful for you to program. Okay, but in the end, when you come down to the operating system level pretty much they don't really understand anything like objects or anything inheritance, all that kind of stuff. Okay, at the operating system level, the only thing they deal with are memory locations, addresses and content of memory locations. Okay, so there might be symbols. Okay, you have a global variable, you have a symbol, you have a function that's also a symbol. So they basically deal with symbols and addresses. There's really no object, no inheritance, no nothing. All right, so in this class, eventually you're going to see, how is it possible that only deal with symbols and addresses? That's enough to build an operating system. You don't really need anything else. Okay. All right, I'm skipping all the history stuff. The next thing we're going to do is we're going to jump into a simple operating system. So this is the introductory material to give you a high-level view of what an operating system looks like. Okay? All right, so as you can see from the outline, okay, that we're going to talk about the structure of the operating system, and then we're going to talk about processes. What is a process, what is address space and threads and stuff like that, how to manage them, and then eventually we're going to show you how to run a program on an operating system. And finally, we're going to talk about the files abstraction at a very high level. Okay? All right, a simple OS, right? In the textbook, when they talk about a simple OS, what they're referring to is something called the 6th edition Unix. Okay, the 6th edition Unix is very simple. The source code was available to university in the 1975, and this code was from Bell Labs. And lots of the publicly available Unix system or things that are based on Unix, they start with the 6th edition Unix. Okay, our kernel assignment, the Unix operating system, is also a derivative of the 6th edition Unix. Okay, and it has a major influence on all the modern operating systems. Okay. The 6th edition Unix is very compact. It fits into 64 kilobytes, not megabytes, kilobytes of memory. So it's tiny. Okay, it's a single executable, completely stored in a single file. Okay, so this is called a monolithic operating system. The entire operating system is a single file. They get loaded into, into memory. Okay, at the time when your operating system boots. Okay, we're going to talk about booting a little bit later. When the operating system boots up itself, it will load this file into memory, and then it will jump into one of the memory locations and say, start running your operating system. All right, so this is monolithic, and it's very compact. All right? Okay, so in order to talk about, what is the operating system structure is that, one of the things the operating system does is that it will execute privileged code. Okay, because you want to isolate the operating system from the user process, so there are things that the user program are not allowed to do. Okay, so these are called privileged instructions. Okay, so the privileged instruction can only execute inside the operating system. Okay, to be more precise is that, on the CPU, the processor, there's something called processor modes. Okay, so they are part of the state of the processor. Okay, so every processor has this thing called processor mode. Okay, and some of the modes are more privileged, and some of the modes are less privileged. Okay, and usually all processor will provide support for at least 2 modes. One is called the user mode, and that's when you are running a user process. Okay, so if you're running your warm-up 1 or your list test, you are running a user mode process. Okay, so in this case, this is the, it has the fewest number of privileges. Okay, so you can only do some very, very simple stuff like running the program and stuff like that. Okay, and then there's the other important mode. It's called the privilege mode. Okay, so this is the most privileged. It's the one that has most privileges. It can do a lot of stuff the user mode program cannot do. Okay, so what can you do in the privilege mode? For example, if your processor wants to talk to an input-output device, a piece of hardware, okay, your operating system can do it. But if you have a user program try to do that, well, you're going to cause all kinds of trouble. Okay? So in the user program, you actually can be very, very smart. You say, hey, I know that my user program is going to be compiled to run on a, x86 processor. So therefore, I can actually program it in such a way that I'm going to execute machine instructions. Okay? In the machine instruction, I'm going to use it to talk to an I/O device. Okay? So if you do that in a user mode, your program is going to get killed. okay? Because you're not supposed to have, you don't have the privilege to execute those kind of instructions. All right, so some machine instructions are privileged. They can only be executed in the privileged mode. And some instructions are not. Those instructions can be executed in both the user mode and the privileged mode. Okay? So what happens in the operating system is that usually is that if you're in user mode, you're running a program, and if you execute a privileged instruction, okay, what's going to happen is that you're going to transfer control into the operating system so the operating system can deal with that to see why do you try to execute that privileged instruction. Okay? Maybe you're allowed to, maybe you're not allowed to. Okay? As it turns out that some of the instruction that it's okay for the user mode to execute, even though those are privileged instruction. Okay? Because that's a way for the user to request service from the operating system. Right? You got to have a way to make requests, say, hey, operating system, do A, B, and C for me. Okay? And the way that you do that is by executing a privileged instruction that you're not allowed to execute. So therefore, you will transfer control into the operating system, and the operating system will, look at that and say, oh, this is what you want me to do. Okay? Or if you try to execute an I/O instruction, the operating system says, no, 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 and it will kill your user process. All right? So the operating system is there to make that decision. All right? Okay, so for 6th edition Unix, the entire operating system will run in the privileged mode, okay, and you're allowed to run user application. But when you're in the, in the operating system, then you have to be running in the privileged mode, okay? Everything else in the application running user mode. For other systems, especially the modern operating system, a lot of the operating system functionality actually run in the user mode. Okay, so it's not a requirement that everything in the operating system has to be run in the privileged mode. Okay, so it's kind of, it can get confusing at times. So therefore, we will use the word kernel to mean the portion of the operating system that run in privileged mode in general. Okay, when we talk about general operating system, right, let's say that you are getting an operating system upgrade by downloading something from the internet, right? Is that the operating system kernel that you're downloading, or is it the operating system you're downloading? Okay, so the general term is that you're downloading this big thing called the operating system, but only a tiny portion of it is called the operating system kernel. Okay, so that the kernel is the one that has to be running in the privileged mode. Okay, so we use the word kernel to mean the portion of the operating system that runs in the privileged mode. All right, and the other junk that you download the operating system, lots of stuff you never use. Okay, they're still part of the operating system, but they're not part of the kernel. Okay. And when we are talking about the 6th edition Unix or this simple operating system, then the entire operating system in the privileged mode. So then in that case, we're using the word operating system and the word kernel sort of interchangeably. All right, so so you got to interpret the word operating system sort of in context, because sometimes it means the kernel, sometimes it means the whole thing. All right. Okay, so what does the operating system look like? Okay, so here is the 30,000-mile view from the top. The operating system looks like this thing, right? So we know that on top there's the user process, okay, and below we have hardware. Okay, the operating system normally, if you're running your list test, you're running warm-up 1. What is the operating system doing? Nothing. Okay, because imagine you only have a single processor, right? The single processor is executing your list test, executing your warm-up number 1. Well, the operating system cannot run in parallel, right? So therefore, the operating system is actually doing nothing when your program is running. Okay, most of the time, the operating system is actually doing nothing. Okay, it's there to provide some kind of a service. It provides an abstraction. It's also sitting there waiting to serve somebody. It can serve the user program. It can also serve the hardware. All right, so from the very, very high level view, the operating system sitting over here, it's waiting to serve someone, okay? The application will call upon the service of the operating system using something called traps, okay? So if you have a user application over here, it requires service from the operating system. So what kind of service does it require? If it's executing instructions, adding stuff, multiplying stuff, it doesn't require the operating system to do any kind of service. Okay, so when does the user application require operating system service? Well, when they try to read or write a file, right? Because the file is an abstraction, right? It could be some disk sitting over here. The user program over here, there's no way to talk to the disk by itself. Okay, so in that case, when it needs to access the file, it needs to invoke a trap into the operating system and ask the operating system, say, hey, could you open this file for me? Could you read 20 bytes from this file and put it here for me? Okay, could you write this 50 bytes of data onto that disk? Okay, which I have no idea where it is, but it's named, according to this file name. Okay, so in that case, your user application is requesting service of the operating system, and that's done using traps. All right, so we're going to see traps, throughout the entire semester. What about the hardware? The hardware call upon the operating system to do via interrupts. Okay, so why would the hardware needs to, go knock knock on the operating system? Knock knock, who's there? Hardware. Okay, so the hardware there is to transfer data. Okay, so for example, right, you have the hardware controlling a disk, and there's some data you need to transfer into memory. Okay, so it can actually do that by itself because memory is hardware and the disk is hardware. So the hardware can actually transfer data from one place to another. Okay, so why does it need to tell the operating system anything? Okay, because why does the the hardware make that particular transfer? Well, it's because the operating system asks it to start a transfer. Okay, so in response to the operating system to the trap, the operating system will ask one of these hardware devices to do some operation, but it doesn't know when it's done. Okay, so therefore, the interrupt is usually there to tell the operating system that say, hey, the last thing that you asked me to do, I'm done. Okay, and the device says, well, what's next? Okay, so during the interrupt, the main thing that the operating system needs to do is to tell the device to do the next thing. Okay, and then also what it will do is that the reason that it started that particular operation on the device is because it's doing that on behalf of a user process. Okay, so the user process is basically waiting for something to get done. It's trying to read, 10 bytes from the disk. If the user process is waiting to read 10 bytes from the disk, what is the user process doing? It's doing nothing, right? It just sit there and twiddle its thumb waiting. Okay, so in that case, to react to an interrupt, what the operating system needs to do is to say that, hey, user process, you're allowed to continue executing because now you have the data. All right, so the reason the operating system, need to handle interrupt is two things. One is to unblock the user process, tell it to continue because the read has completed. And the second thing is to tell the disk, tell the device to do the next thing. All right, and that's what's done in happen during an interrupt. All right, in order for us to talk, more about the operating system, I'm sort of going to explain what a processor looks like. Okay, and this is sort of the basic hardware that we're going to be dealing with. In this picture, we're going to have an x86 processor. Okay, the x86 processor has a bunch of registers. Okay, these registers are very important. You're going to get very familiar with them pretty soon. Okay, so for example, there are different classes of register. One of them is called index register. The other set is called segment register. And then there are a bunch of general purpose registers. And then there's some other registers. Okay, one of the important ones is that in the segment register called the code segment register, CS stands for code segment. Okay, inside the code segment is store the processor mode. Okay, for Intel, the processor mode actually stored in 2 bits. If the bit is equal to 0, 0, that means that you are in the privilege mode. If the bit is equal to 1, 1, that means that you are in the user mode. Okay, so the processor mode is actually stored inside the code segment. Okay, so anytime if you are, if the processor is executing program, executing instructions, then by looking at the bits inside the code segment, then you know whether you're in the privilege mode or you're in the user mode. All right. What other registers are important, right? The general purpose register on Intel is called AX, BX, CX, DX, some very generic names. Okay, so they are general purpose. So if you want to add 2 things together, you put, you want to add 3 and 5 together. You put 3 in register A, you put, 5 in register B, and you say add them together. Okay, so there are these machine instructions that you need to use to manipulate, these registers. Inside the flag register store a bunch of processor flags. So for example, if you add 2 numbers, you get an overflow. Well, one of them is the overflow flag. If you try to add some large number, maybe you want to keep track of carry, one of these bits over here is the carry bit. Okay, so and then there's something called a 0 bit. If the last operation that you perform created a 0, then the 0 bit will be set. Okay, so when you execute machine instructions, some of the machine instruction are, the machine instruction version of if then else, right? In C, we do something like if then else. In machine instruction, you can't really do if then else. What you will do is that you will test one of the bits in the flag register, saying that if 0, I go here, otherwise I execute the next instruction. If there's a carry, I jump to another machine instruction, etc. Okay, so the flag register is basically there to use to control the program. Okay, one important bit of information inside the flag register is interrupt enable. Okay, or sometimes this is written as IE. Okay, interrupt enable. If this bit is equal to 1, okay, what happens is that if the device come and interrupt your processor will actually respond to the interrupt. Okay, if IE is equal to 0, when the interrupt comes, actually your processor is going to ignore the interrupt. Okay, all right. So so that's what some stuff are in the flag register. Okay, another 3 very important register. You're going to see this over and over again, are the EIP. So these are index register. So they use to tell you a location where you're doing something. Okay? EIP is the instruction pointer. It tells you which instruction you're executing. Okay? So if you think about this is your address space, right? This is your code. Program is over here. Okay? Your instruction register always points somewhere in your code segment because it's telling the processor what is the next instruction to execute. All right? So this instruction pointer will point, inside the code segment. Okay? Then there's ESP, is a stack segment. So over here, if you have a stack, okay, the top of stack is actually pointed to by the ESP register. So ESP register will point right here, telling you where the top of the stack is. Okay, why does it need to know where the top of the stack is? Okay, because if, inside this code, you are calling a function, what you need to do is you need to create a next stack frame and push it onto the stack. So the next stack frame needs to be created on top of the current stack. So therefore, you need to know where the top of the current stack is so you can create the next stack frame. Okay? So when you call a function, right, a stack frame is going to get created and ESP is going to point right here. When the function returns, then your ESP basically will point to the previous stack frame, the stack frame of the previous function. Okay? Then, I guess to make things more confusing, there's something called EBP. EBP is called the base pointer, or sometimes it's called as the frame pointer. Okay? EBP is the frame pointer. What it does is it actually points to the middle of a stack frame. Okay? So if you're currently running a function right here, this is your current stack frame, EBP will point somewhere into the middle of the stack frame. All right, it's not exactly right in the middle. What it does is actually inside over here, this location, okay, the stack frame are actually linked together using a linked list. Okay, so this memory location is going to point to the previous stack frame. Okay, and the previous stack frame, again, right in the middle where EBP is supposed to be, will point to the previous stack frame, probably the previous stack frame. Okay, so this way, when you try to run your debugger, you say, where am I? It will actually print out where you are inside the stack because it knows the structure of the stack frame. All right? So therefore, EBP will point to the current stack frame, but it's not always true. So later on, when we go to chapter 3, we're going to see when does the EBP pointer point to the middle of the current stack frame and when it doesn't really do that. Okay? But the idea over here is that it's a very useful pointer to tell you where is the current, current stack frame is. Why do you care where the current stack frame is? Okay, the reason is that remember that for every function, okay, the function argument and the local variable, they live in the stack frame. Okay, so the way that you find these variables that live in the stack frame is that you're going to use the EBP pointer. They point to the middle of the stack frame, and you use that to access, all these local variable and the function arguments. Okay, you don't know the local variable and the function argument. You don't know their absolute address. All you know is their location relative to where EBP is pointing to. Okay, so therefore EBP is a very important pointer because it allows you access into the stack frame so you can get to the local variable and get to the function argument. All right, so that's sort of the, all the register in there. Again, of course, there's right, that I don't mention. The processor talk to hardware versus, using some of these signals coming out of the processor. Right? The processor is a chip. Okay, the chip has a lot of metal contact, and it goes out, and then you can connect them to different places. What the processor normally connect to is something called a bus. Okay, so you might call this the system bus. Okay, you can call it a CPU bus, you can call it a memory bus, doesn't really matter, some sort of a bus. Okay, a bus is just a bunch of signals. Okay, they're grouped together to be called a bus. Okay, so in this case, what happens is that on a 32-bit processor, there are 32-bit of addresses. They go onto the bus to address devices on the bus. Okay, so this 32-bit address go on the bus, and there are also 32 data bits go onto the bus. So if you're trying to write, okay, so on the other side, you have things like memory that are connected to the bus, or maybe a device controller, like your network interface card, like your disk controller, they might be sitting on the bus. Okay, so for your processor to access memory, basically what you can do is that you can put an address on the bus to say, I want to address a certain memory location, and then what you do is that you put the data out there, and then you can write to memory. Okay, so in order for you to write to a particular memory location of the physical memory, what you need to do is you put an address, put a data pattern right out here, and then you need to generate the write signal. You set write equals to 1, okay, and read equal to 0. Then what happens is that the data pattern that you put on the bus is going to get written into memory. Okay, if you want to read a memory location, what you will do is that you put the address pattern over there, and then you set the write equal to 0, and you set the read equal to 1, and that will read that particular memory location going through this data D0 to D31, and those data will go into the processor. All right, so the processor, it's kind of dumb. That all it does is to move data in and out of memory, and then when it go inside the processor, then only at that point, then it can perform, addition, subtraction, multiplication, and stuff like that. It cannot do something like, oh, these are two memory locations, multiply them together. It doesn't work that way. You have to read that data into one of the general purpose register, read another piece of data into another general purpose register, multiply them together. The result, you have to write it back to memory. Okay, so it's very, very, you have to tell the processor to do every little thing. Okay, so that's the address bits, the data bits, the read and the write. And then there's also the interrupt. Okay, the device can actually raise the interrupt signal. Okay, so they will set this interrupt equals to 1, and then the processor will get interrupted. Well, it depends on the interrupt enable flag. Okay, if the interrupt enable flag is equal to 0, then even when a device tries to interrupt the processor will ignore it. Okay, so in that case, that interrupt is called pending. Okay, so when you have a pending interrupt, that means that the interrupt is disabled in the processor, okay, but somebody wants to interrupt the processor. Okay, so this device controller might have important data that has finished transferring and telling the CPU, say, hey, I just finished it, what's the next thing to do? Okay, so you better not disable interrupt for a very long time, okay, because otherwise, what happens is that some other data might override the old data. Okay, so therefore, you shouldn't disable interrupt for a very long time. Finally, there's a signal over here called lock. Okay, when we talk about, I guess, chapter 5, we're going to see how lock is being used. Okay, so one thing that this lock, what it's trying to do is that it will try to lock out the bus. Okay, so this is a physical bus. When you are reading data from memory to the processor or from writing data into memory, okay, that's one instruction. So during the duration of that read and write memory, you own the bus. Okay, when you own the bus, well, there's only a single bus right here. Nobody else can use the bus. Okay, but what if you do two different operations? You read from the memory, and then you write to memory. Okay, so when between the read and write, somebody else can get on the bus. Okay, so somebody else might be this, device controller is trying to write some data from the device controller to memory, or try to read data from memory into device controller. Okay, if you want to prevent that from happening between two memory read and write, what you can do is that you can assert the signal set lock equal to 1, and this will lock out everybody over the system bus. All right, so later on we're going to see how that is useful. Okay, so basically this is a summary of all the CPU signals. All right, so we're going to come back to that, picture, many times. All right, so trap. So let's talk about traps and interrupts. Okay, trap are a general way for invoking the kernel from user mode. Right, so the user is trying to ask the kernel to do, the operating system to do something. Okay, so what it will do is to generate a trap. Okay, but usually trap can also be caused by errors. Okay, for example, if your program execute, if you say 3 divided by 0. Okay, so 3 divided by 0, so you say x divided by y, right? Z equals to x divided by y. And turns out y is equal to 0. Okay, what is your processor supposed to do? Okay, this is an illegal instruction, right? Okay, so they can't really execute this instruction. Okay, so what happened is that at that point, your user process can no longer execute. Okay, so as a result of executing this machine instruction, is that you have to transfer control into the kernel because only the operating system kernel can deal with this because your user process just did a no-no. Okay, so therefore, in this case, you will trap into the operating system. By executing a divide by 0, you will trap into the operating system, and the operating system will decide what to do. Okay, in this case, what should the operating system do? I mean, you did a divide by 0, right? Should your program continue to execute the next instruction? No, right? So the operating system will kill your program. Okay, if your program is doing star p, okay, you say x is equal to star p, and p turns out has the value of 0, so it's a null pointer. You're trying to dereference a null pointer. Okay, and again, this particular instruction is going to cause an error. You will trap, as a result of executing this instruction, you will trap into the operating system, and the operating system says, well, you are not allowed to continue because you just produced an error. Okay, so usually, right, some of the reason you generate a trap because you execute some illegal instructions. Okay, so these are really not privileged instructions; they're just simply illegal instructions. So you get trapped into the kernel. Okay, but they don't really have to be. All right, it could be, that you're making a system call. All right, so for example, if I try to, to do a read from the disk, okay, I'm going to make a read call. Okay, I cannot do read myself. I'm the user program, right? So therefore, I have to ask the operating system to do read for me. Okay, so what happens is that inside the implementation of read is a system call. It's just a C function. When you make this particular call, eventually it will call a particular machine instruction, and the name of that machine instruction is called trap. Okay, so for the x86 processor, there's a machine instruction called trap. So basically, any kind of a system call is kind of like a wrapper around a trap machine instruction. So what it will do is that it will set up, parameter that you want to pass into the operating system kernel, okay, and then invoke the trap instruction. When you invoke the trap instruction, it's like an error. You're going to trap into the operating system. The operating system says, hey, how did I get here? Oh, it's because you execute a trap machine instruction. Okay, so then at that point, it knows that you want service from the operating system, and then it will do the right thing. Okay, so when you get into the operating system needs to determine whether you have just executed a trap instruction, or you execute a divide by 0, or you execute a reference to a null pointer, and then it can decide what's the appropriate action that has to be done. All right, so trap always elicits some sort of a response. For a programming error, you kill the user process. Okay, if it's a request for the operating system to perform some service, the operating system has to start that particular service. Okay. All right. There is something else called an upcall. Okay. So it is possible for the operating system to actually so the trap is like the user program calling the operating system, right? It's like a function call. Okay. And certainly when you call the read function, it looks like a function call. Okay, except it goes into the operating system kernel. Okay. We can actually go the other way for the operating system to call a user function. Okay, it's kind of weird, right? Why would the operating system call a user function? Okay, normally operating system just stay there and do nothing. Okay, so what happens normally is that the user program may specify a handler to be invoked in response to an error. The user program says, when I divide by 0, I know I'm going to divide by 0, so it's okay don't kill my user process, call this function instead. Okay, so that's called a signal handler. Okay, so the user says, divide by 0, no problem, I will handle it. You don't kill my process. Okay, so in that case, what happens is that you're going to trap into the operating system, and the operating system actually going to make that function call on your behalf. Okay, so that's called an upcall, right? Because the operating system is staying at the lower level. It's going to call up to the user process and execute that particular function as if it's the user process. All right, so this is the upcall mechanism, and on Unix, the way that you provide, that you perform upcall is called signals. Okay, and when you're working on kernel, one more number, assignment number 2, you're gonna be able to handle signals. Okay, so for example, you're running your program, right, and then the program somehow went into infinite loop. You press Control C. Okay, so Control C is going to be delivered as a Unix signal. And then your program can say that, oh, when the user press Control C, don't kill my program, call this particular function instead. All right, so we're going to see that, when we handle Control C. All right, and this one already mentioned, right? System call is just a wrapper around a trap machine instructions so that you can trap gracefully into the kernel. Okay, because the transition from the user space into the kernel needs to be done very, very carefully. Okay, if you don't do it carefully, when you try to transition into the kernel say, hey, something's wrong, and just kill you. Okay, so in order for you to do this carefully, the operating system developer developed the system call so that right before you execute a trap instruction, you can do everything else properly. All right, so that's why we provide these system calls. All right? Okay, interrupt, right? Interrupt is, by definition, they're hardware. Okay, they come from the hardware, right? So it's a request from the external device for response from the processor. Okay, so if you tell the disk to go ahead and read some data for you, right? Your user process, you call read system call, and the system call turn into a trap. You'll go into the operating system. The operating system start off the disk to transfer some data from a particular disk into a memory buffer. Okay, that might take a very, very long time, right? In the meantime, your user process got put to sleep. So the operating system is running some other user process. Okay, eventually when the disk is finished, it's going to interrupt the process. It's going to interrupt the processor. Okay, what is the processor doing at that time? Right, so your processor, is executing other programs. Okay, so chances are, right, when the interrupt happens, it's not the user program that requests that interrupt, okay, that was executing in the processor, right? The user program that requests that disk transfer, that user program is suspended, it's sleeping. Okay, so chances are, the interrupt, as the interrupt happens, whatever the processor is doing has nothing to do with whoever generated the interrupt. Okay, those two things are completely independent. Okay, so therefore it says over here they're handled independently of any user program. Okay, it's just an interrupt, just happened at a random time, and now the operating system need to handle it. Okay, it doesn't really matter who is the current running user process. Okay, it could also be that currently the operating system is running. Okay, so the interrupt is basically come at a completely asynchronous time. Okay, it's kind of hard to control exactly when interrupt happened. It just happened out of the blue. Okay, so if you try to control it, it's a mistake. So don't try to control it. It just let it happen. Okay. Okay, so the response to an interrupt may or may not directly affect the current running program, and most likely it has nothing to do with the current running program. Okay. All right. So by definition, interrupt are coming from hardware, but unfortunately, there's something called software interrupt. Okay, it might be very confusing sometimes. The software interrupt, they are generated programmatically. Okay, they are not generated by a device, and this is done by executing an interrupt machine instruction. There's actually a machine instruction in Intel, it's called INT, and it will cause an interrupt. Okay, so in that case, if you execute this instruction and generate interrupt, well, that's called a software interrupt. It's very different from the hardware interrupt because it's not generated by a device, and this one is related to whatever you're doing currently in the processor, right? It's the processor that just executed this instruction called the INT instruction that caused this software interrupt. Okay, so in that case, yeah, it's related to what the processor is currently doing. Okay, so this is very different from hardware interrupt. although the mechanism for handling interrupt are very, very similar. Okay, and as it turns out, the mechanism for handling both trap and interrupt, they're all very, very similar, right? Because in the end, what you want to do is that you want to get the operating system's attention. All right, so therefore, they all have the same mechanism. All right, so that's the basic operating system structure. Okay, the next thing we're going to talk about are, processes. All right, so if you have a program you want to run, what do you need? Okay, so over here it says the fundamental abstraction of program execution, you need memory, okay, to run your program, and you need processor to execute your threads, and then the third thing you need is something called execution context. Okay, so the execution context is a little weird, right? Memory is kind of obvious, right? We use the address space to represent memory, right? That address space that we saw before, okay? So they represent all the memory location that your program have access to, okay? And again, recall that process is an abstraction of memory, and this address space belongs to the process and not belong to any threads. Okay? All the threads inside the, one process, they share the entire address space. Okay? It needs a processor, but the way that we're going to abstract away the processor is to use threads to abstract that away. Okay? And finally, the execution context. What is that? So
the time is
the execution
10 o'clock.
context is really important. It's important in the sense that if you want to suspend your program, right? You have a program that are running, right? Using a single user using a process and a bunch of threads. Okay. Now you want to suspend all the threads in this particular process, or if you want to suspend one of the threads. Okay. If you want to suspend this particular thread, well, why do you want to suspend it? Okay, because you got an interrupt, you got whatever. Okay, and then later on you want to resume the execution of the thread or all the threads inside this process. Okay, if you want to resume the execution of this particular thread as if nothing got interrupted, so basically what you need to do is you need to store the current state of your process and your threads into some place, and this place is called the context. Okay, so right before you're going to suspend your thread, you need to save the context into some area, and later on when you want to resume that thread, you need to restore the context back into that thread. Okay, so this context, what do you really need in order for you to resume the execution of a thread? Okay, so if we go back to the previous picture of the processor, well, for this thread to be continued to executing, right, it was executing something, inside the processor it has some states, okay, now you want to suspend the execution. So basically you need to take all the register in your process, all the register in your processor and then store it into the context area somewhere. Okay, and then you can run another thread, maybe another thread belongs to another process. But eventually this thread is ready to resume again. You got to go into the context area, read everything back, and put it inside the processor. Okay, so when I say restore the execution context, that means that you go to memory, take the execution context, and put it back into the processor. Okay, and then when the processor resume running again, then it will go to the state exactly where it got suspended. Okay, so that's one place to store the execution context. Is to store that means that this piece of memory called the context of the thread or the context of the process. Okay, but what about other stuff? Okay, so for example, if you have opened a file, you have read 20 bytes from the file. Okay, and next time when you try to read it, you should start reading from where you left off. Okay, so that particular file also have a context. Okay, the context is that you have read the first 20 bytes, so the next read will start from location 20. Okay, that information also need to be stored somewhere. Okay, so if you think about a file, you can think about a network, all kinds of stuff. Anything that the process uses, you need to keep track of the context for everything. All right, so it's very important, so the execution context is sort of a very important concept that when you want to suspend a thread or process, you need to make sure that all these information got kept in memory somewhere, so later on you can resume execution. All right, so it's a very vague term. Basically, it says, well, everything that get involved, you need to be able to save them and be able to restore them. All right. Okay, to deal with processes, we're going to look at some of the APIs so that we can also understand exactly what a process is. Okay, the one we're going to look at is called fork, exec, wait, and exit. And these are basically the 4 APIs that you use, and these are all system calls. Okay, they are used to maintain information about a process. Okay, some of the stuff in the process are handled automatically, and there are these things that you can do explicitly to ask the operating system to do something for you. All right, so let's look at a very simple program. This is a program that generates a bunch of prime numbers, right? So I'm not going to go through any detail. So you just believe that this is the program that generates prime numbers, and then it will generate prime numbers, put it into this array. When this program finished running, this n prime is going to be equal to 100. So inside this array, you will have 100 prime numbers in them, starting from 2, 3, 5, 7, etc. Okay. I'm going to also use this slide to introduce my, color code. Okay, any of the reserved words in C is going to be written in blue, right? Const, int, for, all that kind of stuff are reserved keywords. The numeric strings and constants are in red, right? 100 is in red. If you have any kind of a string, they will also be in red. Okay, comments are in green, and black is everything else. All right, so whenever you see my code, this is going to be the color code. One of the abstractions, so if you have taken like the algorithm class, you've probably seen something called a Turing machine. Okay, so Turing machine is kind of sort of a computer science theoretic abstraction of what a running program is. Okay, and in the Turing machine, it sort of describes a Turing machine using a picture like this. Okay, a Turing machine consists of 2 parts. So this is enough to represent any executing program. Okay, it's a very simple and very powerful abstraction. Okay, is that you have an infinite tape. Okay, this tape go infinity to one way and infinity goes the other way. Okay, so this one is basically it's an abstraction for memory. Okay, and then over here you have an abstraction for the processor. This is the machine that knows how to execute stuff. And inside this machine, you can store some state information, just like our x86 processor has a bunch of registers that can store information. Okay? So this simple abstraction has some rule that it has to follow, and this is enough to represent any running program. Okay? So the rule is that you can only do things one at a time. Okay? At every timestamp, what you can do, you can read the stuff under the machine. Okay, read that data into the machine, into the processor. Okay, or what you can do, you can perform an operation over here, or you can write that some data onto the tape, but you can only write at the current place where your machine is over. Okay, and finally, there's only one more thing you can do, is that you can move your machine to the next location. Okay, you can move 1 down or 1 up, but you can only move 1 location. Okay, and this is basically what your program is doing. All right, so this very simple abstraction sort of tells you that you can actually have infinite storage, but this particular machine has finite number of states, so this is the finite state machine. All right, and that's what a program is, infinite storage running on a finite state machine. Okay, so how do you reach infinite storage? All right, if you think about our address space, right? Our address space has code, right? Okay, and have data, have stack, and have heap and stuff like that. Okay, you can name everything, right? All these locations over here, you can give them names. When you give them names, basically what you're doing is that you're specifying stuff in the data segment. Okay, data segment are the stuff that are global variable. Every global variable has a name, right? So you can name location on this tape, but that will not take you to infinity. Okay, you can use the stack, but the stack only grows a certain amount. Again, you can use some location over here. Okay, so how do you reach the stack? Right, as I mentioned before, you use the EBP register. Okay, so inside the processor there's the EBP register, so it knows sort of where things are. It can use that to move around the tape to access those memory locations. All right, so you can name things directly. You can also use an array, right? If I have an int array, a something like that, 300. Okay, basically that would declare some parts of this tape to be storing value for this particular array. Okay, again, that will not take you to infinite storage because, if you have an infinite array, well, there's no way to stay in C. Okay, so therefore you can't really do that, right? So the final thing that you have to do in order for you to reach a lot of memory location is to use indirections. Okay, so in C, we have pointers. Pointers is a way that for you to reference one of the memory locations. So in the data segment, over here, you can reference an object, in the heap. Or in the stack segment, you can also reference object in the heap. And inside the heap, you can point to another object in the heap and another object in the heap. Okay, and also in your address space, you need to keep track of the files that you have open, right? So the files that keep track of somewhere else. So over here, you got to have a way to reach the files that you're keeping track of. Okay, and again, that's one level indirection. Although this level indirection is not done through a pointer. Okay, it's done through a file handle. Right, so over here, this is called a handle. I guess file handle. Okay, using a file handle, you can also reach additional memory location. Okay, and once you get to a file system, you can have a large disk. So now things starting to look like infinite storage. All right, so in order for you to sort of realize this, this abstraction, one of the very important things is indirection. All right, and we're going to see indirection get used many, many times in this class. So here's one of the reasons we have to use indirection to start with. Okay? All right. So Unix address space, we look at a little more detail. The data segment actually is divided into two different segments. One is called data, and the other one is called BSS. Okay? The data segment contains initialized data. So if you say int, p is equal to 5, and if this is a global variable, then p lives inside the data segment. Okay? If you have another global variable, q semicolon, this is the uninitialized variable. The uninitialized variable turns out live inside BSS. So what happens is that q is sitting right here and has no initialized value. Okay, while p over here is a memory location that started out with a value of 5. Okay, so it turns out it's important to distinguish them, as we see later on why this has to be separated out. All right, and all these memory locations, they are part of the tape of the Turing machine. Okay, so if you look at this particular program, right, so we sort of modify the program a little bit. Okay, the n primes over here, we intentionally don't initialize them. So this particular variable can be found in the BSS area. The prime over here is going to be a pointer, okay, because what we end up going to do is that we're going to point it to the heap memory. Okay, so over here, the prime, over here, here's the data segment. Okay, and here's BSS, right? N primes is here, and primes, they're living both here. All right, so inside this one, instead of using an array, we're going to use dynamic memory allocation. We're going to call malloc. We're going to call malloc to allocate this many integers. Okay, so over here inside the heap area, right, this is the heap area. Okay, when you make this particular call, if n prime is equal to 100, okay, and the size of n is equal to 4 bytes, okay, on a 32-bit processor, so you're going to allocate 400 bytes right here. Okay, and then you're going to return the memory address to be pointed to by prime. Prime is right here, so this guy basically going to point to the first location inside this block of memory. All right, so this particular exercise basically tells you where all these data, where they're supposed to sit. Okay, and then and for this class, you need to know where every variable is. Okay, you need to know whether it's in the stack, in the heap, in the data region, in BSS, because later on you need to follow all these objects. This program also uses argv1. Okay, argv1 is get passed into the main program. Okay, so therefore inside the stack frame over here, the first stack frame is main. Okay, inside main there's argc, and then there's argv. All right, so this guy actually is sitting in the stack somewhere. Okay, so they all have different memory addresses, right? This one has very high addresses, argv and argc. The global variable has low addresses, and the heap has medium addresses. All right, so this one fill out this particular array with that particular data. Okay, this program is not very interesting. It computes all the values, but it doesn't really do anything to them. Okay, so you don't really know if the program run correctly or not, right? The only thing you can do is run to the debugger and examine the memory location to make sure that it computes the right stuff. All right, but anyways, you need to know where these variable goes. All right, how do you create a process? Okay, so in Unix, to create a process is deceptively simple, and there's only one way to do it. Okay, if you want to create a process, you need to make a copy of a process. Okay, if you have a process, you can make a copy of it, right? So of course the question is, where does the first one come from? So the first one is a little tricky. The first one appears out of nowhere. Okay, but once you have the first one, from that point on, anytime you want to create a process, you need to make a copy of one of the current existing processes. Okay, so if you have a process that gets created this way, this is called the parent process, and this is called the child process. Okay, so the processes have parent and child relationship. And for you to create a process, what you do is that you invoke the system call called fork. Okay, fork. If you do so, anytime you want to see what a system call do, you should do a man. You should do a man on it. So on Unix, you do man, F-O-R-K. Okay, to look at the man pages of fork, and inside the man pages are have very standard format. Near the top, there's a section called synopsis. In the synopsis section, it tells you what the function prototype of this function is, and also what kind of include file you have to use if you want to call this function. Okay, so the fork is a function that takes one argument, or takes no argument, because the argument over here is void. That means take no argument, and return a single data type that's PID underscore T. Okay, so this is the process ID type, and it's a 16-bit integer. All right, so the fork API returns a 16-bit integer. Okay, so what you do is that the parent process will call fork. Okay, and as a result, you will create a child process. Okay, and this particular call is a system call, so that means that the parent process, when it calls fork, the parent process will be suspended. Okay, it will generate a trap into the operating system, and inside the operating system, you create the child process. Okay, when you create a child process, what do? Well, you have to return back to the parent process for it to continue to execute the next instruction. Okay, you have to return back to the child process, so the child process can also execute, because the child process is an exact copy of the parent process. Okay, it's so exact that the child process, when it continues to execute, it will execute as if fork has just returned. Okay, so in every way, the child process is an exact copy of the parent process. Okay, the current instruction pointer actually of the child process is going to be pointing to exactly the same location as the parent pointer. So when this guy executes, it's going to be as if it returned from fork. Okay, so the only way that you can tell whether it's a parent process or a child process at that point, right? Because now both processes will start to execute. Okay, they all point exactly the same thing. All their address space are exactly the same. So how do you tell which one is parent, which one is child? Okay, the way that you tell is by the return value of fork. Okay, in the parent process, the return value is going to be the process identifier, or PID, of the child process. In the child process, when the fork returns, it will return 0. Okay, so basically you check the return code of fork. If it's equal to 0, then you know that you are executing in the child process. If you return in something that's not 0, then you know you're executing in the parent process. All right, so over here, this picture says, this is the address space. You make an exact copy of the entire address space. All right, so that's a very expensive operation. Later on in Chapter 7, or when we go kernel 3, we're going to see exactly how this is done, so that it can be done very efficiently. Okay, because if this is a 32-bit address space, that's 4 gigabytes of memory. You want to copy 4 gigabytes of memory, that will take a very long time. Okay, if you do that, your operating system is not going to sell very well. All right, so when do you want to do something like this, right? So for example, if you're implementing a login shell, okay, if you secure shell to Nunky, right, you're running /bin/tc shell. By default, you're running the C shell, okay? You type the command ls, right? You want to list the directory content of the current working directory or the home directory. So you type ls. So what happened in that case is that the parent process is going to be your login shell, okay? It will fork off a child process, which is an exact copy of itself. So the child process is also the login shell, right? So at this point, the child is also the login shell, okay? And then on top, on the child process is that, oh, I'm the child process. What I will need to do is that I will load the program ls into my address space. Okay, so at this point, what the child process will do is it says destroy the entire address space that you just gone through all the work to copy, destroy the whole thing, and now load on top of my address space the bin/ls program, and then go jump into the main program. Okay, so this is how one program runs another program, where your login shell is the parent program, it spawned off a child process, and then overload /bin/ls into the child process, and then you're running that program. Okay, and this program will start running, right? Do a directory listing. When it's done, then it will get terminated. All right? Okay, so create a process, right? Picture looks like this. Okay, over here in the code segment, there is a function called fork, the system call. Okay, so EIP of the processor will be pointing to this one, what they call the fork. Okay, and then fork is a wrapper around the trap system call. So eventually, you're going to trap into the operating system. Okay, and at that point, the operating system will create a child process. The child process will look exactly like the parent process, except that fork will return 0 over here, and fork will return the PID of the child process in the parent. All right, so inside the kernel, to keep track of processes, the kernel uses a data structure generally known as the process control block, okay, or PCB. Okay, so the parent process control block, the process control block is actually pretty big. There's a lot of stuff in them. Over here, we're going to show a few things. Okay, it contains the process ID of the process. Okay, so again, this is a 16-bit integer. It has a linked list of terminated children. Okay, so when a process is running, it might fork off, to create a bunch of child processes. When the child processes dies, they will get on this list. Okay, when I say they will get on this list, well, their process control block will get on this list. Okay, so this guy will have a linked list of dead child number 1, dead child number 2, etc. And if one of these things is a process control block, so here's the process ID of the first dead child. Here's the process ID of the next dead child. Okay, this guy can also have terminated children because this particular process might also create, fork itself and then create child processes. So they all have the same thing. All right. So the third field over here is called link. Okay. So link is basically the next pointer, right? The next pointer. Okay. It's the next of what? Okay. As it turns out, the process control block only has a single field called next. Okay, so this particular process control block can only belong to one list. Okay, it cannot belong to multiple lists. Okay, so in this case, if the child is dead, then it goes to the parent's dead children list. Okay, so therefore over here, the link field will point to the next dead child for the parent. Okay, if this particular child is not dead, it's running, and is waiting for the processor, then what it will do is that it will get on something called the run queue. Okay, the run queue is the queue that are waiting for the processor. They're trying to get a hold of the processor so they can run again. So in that case, the link field will point to the next guy on the run queue. Okay, if this child process is sitting waiting for I/O, what it will do is it will get on a list of the I/O queue, and then in that case, the link field will point to the next process that are waiting for that particular I/O device. All right, so the link field just points to the next. And depends on what queue, what list it belongs to, while the link field will point to the next guy on that list. All right, so it's a little weird. They basically use the link, in different lists. All right, so over here, for the terminated children list, the link will point to the next dead child for the parent. And then the next field is the return code. Okay, so what happens is that if you have a parent, you create a child process, you ask the child process to do something. when the child process finished, it needs to report to the parent whether something was done successfully or not. Okay, so that's done by using a return code. Okay, so the parent has a return code over here. Okay, so that when it dies, it can tell its parent what the return code is. Okay, so in this example, this dead child number 1, has a return code. So when it finishes executing, when it's done, it needs to set the return code, and then it will go on the parent's terminated children list. Okay, so this way, the parent can traverse this list to retrieve the return code for every dead child. All right? Okay, so the code, we're going to look something like this. So we're going to see the parent and the child executing in parallel. Okay, so over here, this example, in the parent process, is going to make this particular call. Okay, so who's writing the code for the child process? Well, it's the same program. Okay, the parent and the child are executing using exactly the same program. Okay, so over here, the parent process is right here. Okay, it execute fork, and fork is going to return a process ID over here. So over here, I say short. It's a 60-bit integer. It's compatible with the process ID. Okay, so this one says if PID equal to 0, I'm going to execute code right here. If PID is not equal to 0, then it goes into else part. I'm going to do it over here. Okay, so if I do code like this, what happens is that the child process will execute this code, and the parent process will execute that code when fork returns. Okay, so when you are calling fork, you trap into the operating system. Operating system is going to create a child process. Okay, when the child process, when it returns, it's going to realize that the fork is going to return 0, and it's going to go right here, and the parent process is going to execute this code. Okay, so both of these code are in the code segment, right? Okay, but from this point on, they will actually execute 2 different code. All right, eventually the child process over here says some code is here for the child to execute. Eventually when it's done, in order for it to set the return code, what it will do is that it will call exit. Okay, so for a process to set the return code, it calls exit, and exit, whatever the value that you specify over here, this is the number that goes into the return code right here. All right, and after it does that, that particular process is considered dead. Okay, but that particular process is considered dead. So when you call exit, that particular process is process control block is going to get on the parent's terminated children list. The return code is going to be copied over here, but this data structure is still hanging around. Okay, why does it need to hang around? Okay, so actually when you call exit, inside this data structure, there's a bunch of other stuff. Everything over here can be freed, except the process ID cannot be deleted, and also the return code cannot be wiped out. Okay, the reason is because that when the child call exit, and if you think about a single processor case, right, only the child is executing. Okay, so therefore, what is the parent process doing? Well, sleeping, right? Because you can only do one thing at a time. So if the child is calling exit, I mean, the parent process is sleeping somewhere. So if we go and set these values, the parent process is not going to see it. Okay? The parent process will see it at a later time. Okay? So these things can only be freed up when the parent process has retrieved the return code. So how does the parent process retrieve the return code? Okay, there's another system call that it can do. It's called the wait system call. Okay, the wait system call, this is the function prototype. Okay, it returned a process ID for a dead child. Okay, so this particular wait system call basically is to go through the process control block, walk down the list, and start returning the return code for every child process that are dead. Okay, so what it will do is it will return the PID of the dead child in the return code over here. It will also return the return code inside this field over here. Okay, so for the wait system call, the single argument that it has is the address of a status. Okay, and status is, so this is int, so this is return code. Okay, so in that case, what you can do is that you can actually call it this way. You declare a variable int for the return code, and then you pass the address of the return code into wait. Okay, the address of return code, that data type is compatible with the integer pointer. So therefore, you can use this, use this method to receive the return code from the system call. Okay, so inside the implementation of the wait system call, what it will do is that it will go here, get the PID, and get it to be ready to return from wait, and also copy the return code into the argument of the wait system call. Okay, and only at that point, when the operating system is finished with this particular dead child, then it can completely free up this data structure. Okay, so until the parent process execute the wait system call, you need to keep this guy around. Okay, when you, and in this case, you can actually return this guy one at a time. So therefore, this code will go in a while loop. It says while PID is not equal to wait return code. Okay, it's going to continue to call this over and over again. So if you have many, many dead children, every time when it returns, it's going to return the process ID and the return code, and then it go to the next one, and go to the next one, and go to the next one. Okay, so in this case, what it was trying to do, okay, thank you, it's trying to look for the process ID that you are stored over here. Right, remember, the parent take this, this particular path, so when it fork off the child, it remember what the process ID for the child is. Okay, so in this case, it's looking for a dead child of that return code. If the child is still running, then what happens is that this particular system call will block. Okay, so if you go back to the previous picture, if this list is empty, the parent process will block waiting for a child to die. Okay, eventually when the child dies, PID is returned, the return code is returned, this data structure is freed, and it moves to the next guy. All right, you can see that, so this picture is a little weird, right, because you have both the parent and the child, they're both executing in parallel, and the parent is waiting for the child to die, and eventually when the child called exit, that's when these things happen. Okay, well, when the child called exit, it hang the process control block onto this list, and then when the parent called wait, that's when this thing gets destroyed. All right, the sequence of these operations is very, very important. Think about the case you only have a single processor and see how this thing can be done. All right, so when the child called exit, okay, the child is known as going into a zombie state, waiting for the parent to call wait. Okay, because what happened is that, the process ID is a 16-bit quantity, so, if you start creating a lot of processes, the process ID actually will get reused. Okay, so you don't really want to destroy your process control block and reuse that process ID right away, because later on the parent process may get confused when they try to get a process, when we try to call wait, it gets a process ID back, but now this process ID maybe belongs to two different processes. So which return code did they actually get? Okay, so therefore it has to hold on to the process control block for the dead child process until the parent is ready to receive the return code. All right? So that's why the child process has to go into the zombie state. So the next thing is to load a program into the process. Okay? How do you do that? Right? So we talk about you fork off a child process and you load the program into the address space. Okay? The system call that you need to use is something called exec. So it turns out there are tons of functions called exec. So over here we say, well, you're going to use a family of system call known as exec. Okay? So what it will do is it will tell the operating system to load a program into the address space of the current running process. Okay? So it's going to sort of look like this. Okay? After you do a fork, right? In this case, the child process will call exec-L. Okay? The exec-L is one of the exec, system call. You tell it which program you want to execute, what to call this program, and these are the arguments that you need to pass to the program, argv and argcs. Okay? So in this case, if you look at, if you do a manual exec-L, you will see that exec-L has a function prototype like this. And one of the function prototype over here says the argument actually doesn't know how many arguments it has. It put the ... This is called the variable number argument. You can actually put as many arguments that you have, but all of them has to be strings, or it has to be C strings, and the last one is going to be a 0 to show that you have terminated all the arguments. Okay, I got 1 minute. All right, so what happened in this particular case is that before you call exec, okay, so this is going to be the child process. The address space is going to look exactly like the parent process, okay? and then you invoke exact program arguments. You're going to go into the operating system. The operating system is going to wipe out the entire thing, build a brand new address space for the child process. So now this is going to be the new child. Okay, so this is basically going to be loaded on top of the current address space, and the current address space is completely cleaned out. Okay, and then what you're going to do is that you're going to put the main program right here, and you're going to start calling the main program. Okay, the instruction pointer is going to be pointing to the new text segment. This is, in the example, this is the primes program. So we start executing over here, loading the data segment, BSS, and all that kind of stuff, and start executing the main program. All right, so next time we'll continue from here.
This has been CS 402 on Wednesday, May 28th, 2014.